Chemistry powers today, but courageous chemistry is shaping our tomorrow. It's fueling the hydrogen economy and driving clean energy. It's in our semiconductors and even powers our 5G. It makes bridges stronger and medical equipment safer. Chemistry powers progress and binds us all together. But there's something more that sets us apart. Courageous chemistry.
Hello, welcome to another interesting and important class for today. In today's lesson, we'll be looking at separation techniques. When we talk of separation techniques, you already know from our last class what mixture is, elements, and compounds. You know the difference between compounds and mixtures, and we said that we can separate mixtures into their various constituents using separation techniques. So I'm going to learn some of these techniques in this lesson. We'll begin by looking at the first one for today. Remember, I gave you the list of them before. So we'll begin by looking at the first one, which is called sieving. Okay, sieving is a separation technique that is used to separate solid particles of different sizes or based on their sizes. Okay, we make use of an equipment known as a sieve. A sieve is what we locally call filter at home, is it not? Yes, it has holes or tiny pores which allow the particle size with smaller units to pass through the sieve, while those with larger units to stay at the sieve. A very important application of sieving is in water industries and garri production, is it not? Yes. The next one is called magnetic separation. Magnetic separation is used to separate components of mixture, okay, that are magnetic from those that are non-magnetic. Remember, we said the strongest force area of a magnet is called the pole, or the area in which the magnetic force is stronger is called the pole of a magnet, is it not? Yes. So magnetic separation is used to separate substances that are magnetic, such as iron, from substances that are non-magnetic, such as aluminium and zinc. Magnetic separation is widely used in industries that recycle metals like aluminium and iron, of course. The next one is decantation. Decantation is used to separate an insoluble solid from a liquid. Okay, the process involves carefully pouring the liquid from a container to another container while making sure that the solid do not follow suit. Decantation is considered an inaccurate method of separation because of the probability of making mistakes or pouring both the solute and the solvent in the same container. The next is called centrifugation. Centrifugation is used to separate an insoluble solid from a liquid using a machine or a device known as a centrifuge. This machine spins so that the suspension particles separate, and when it stops spinning, the heavier particles settle at the bottom, leaving a clear solution which is easily decanted. So basically, centrifugation uses both the machine and decantation as well. It is applied in a situation where the samples is small quantity, and then areas where it is widely used is in hospital. It is used to separate blood cells from the plasma membrane. You must also note that during centrifugation, equal quantity of water is used to counterbalance the sample in the centrifuge. Alright, take note of that. Pay attention to this lesson to learn more about other
which
techniques.
is used for separating out a liquid from a solution. For example, we could use simple distillation to separate pure water from seawater. Before we cover how it works though, we need to be familiar with the equipment. First, we have a flask that contains the solution, or the liquid mixture, that we're trying to separate. And the flask is sealed at the top with a bung, so that no gas can escape. We then put a thermometer through the bung so that we can measure the temperature inside the flask. Next, we have our condenser, which consists of a main pipe surrounded by a water jacket, which contains a stream of continually flowing cold water, with the water being fed into the water jacket at the bottom and coming out at the top. Then beneath the end of our condenser, we'll have some sort of beaker to capture our pure liquid. And finally, we're going to need some sort of heating device, like a Bunsen burner, which we place under the flask. Our first step is to heat up the mixture, so that the liquid that we want evaporates. As it rises to the top of the flask, the pressure will force it down the condenser. And because we're pumping cold water through the water jacket, the vapor will cool and condense into liquid form, which will then run down the pipe and collect in the beaker. So in our case, as we heat the seawater, we'll get more and more pure distilled water, until eventually all we have left in the flask is salt. Now imagine instead that we were trying this technique with a different mixture, one containing some different liquids, like methanol, ethanol, and propanol. Because these liquids all have similar boiling points, when we heat them, more than one of them will evaporate, and so they won't be separated into pure substances. In this case, we'd have to use a different technique, called fractional distillation, which is the main technique used for separating mixtures of liquids. The equipment for this is pretty similar, but instead of the gas passing straight from the flask into the condenser, the vapors have to first pass through a fractionating column, which has two key features. One is that it's full of little glass rods, which provide a really high surface area. And the other is that because the column is so tall, it's actually cooler at the top than it is at the bottom. To understand why this is important, let's imagine that we were trying to separate those three liquids that we mentioned before: methanol, ethanol, and propanol, which all have similar boiling points, although you don't need to remember them. And before we continue, just be aware that in real life, these would all be colourless, not green. We're just showing them as green to make it easier to follow along. Now, because methanol has the lowest boiling point, we'd heat the mixture to around 65 degrees first. This would cause the methanol to evaporate, and then rise up the fractionating column. It would then pass into the condenser, and condense into liquid methanol, which we would then collect in our beaker. However, just by chance, some of the ethanol, and maybe even propanol, would also evaporate. But as they rise up the fractionating column, and come into contact with all of those glass rods, which are much cooler than their boiling point, they'd condense back into liquid form, and fall back into the flask. This means that the only liquid that will get out the other side will be pure methanol. The next step would be to do the same thing all over again for ethanol, by raising the temperature to around 78 degrees Celsius, which would allow us to evaporate off the ethanol. At this point, all that should be left is the propanol. So we could just assume that what we have in the flask is pure propanol. Or we could raise the temperature again to boil off the propanol, just to make sure.
Alright, what we have here are two beakers, each containing a dissolved aqueous ionic compound. In the beaker on the left we've got magnesium sulfate, and you can see that that is a clear and colorless solution. Looks just like water on first glance. And over on the right we've got sodium hydroxide, which is also clear and colorless. Again, looks just like water. And what we're going to do here is we're going to mix these two and see what happens. You can see a white cloudiness forming right away, and what that cloudiness actually is the product of this reaction, there's actually a solid produced, and it's called a precipitate. And there's these very small particles that are suspended in that right now, but if we let this settle out over time, we'd find that they collect on the bottom as a solid.